So let me start by apologizing to the first lab group. Those who had the lab early on Mondays were in there a little bit long. Sorry about that. Partly because we hadn't talked about some of the things that we'll talk about in the lecture. But even aside from that, we've found ways to speed up the amount of time it takes on this lab. I think there was one section that a lot of you got stuck on for a while of just coding up the Fourier transform and labeling it properly. And so the TAs now are speeding that part up. I think the evening session of the lab finished in the amount of time allocated. And so I hope it'll be much smoother for the rest of you. Sorry to the first session. But I think it's a good lab, a good learning experience, and it'll go well with what you're learning here. Bring some of these concepts to life, hopefully. Okay, so let's first talk about how just the concept of representing a signal in another, with a new representation. We sometimes call this a different domain. This is a concept you're familiar with from, for example, calculus. Let's just talk about the Taylor series as an example. And you'll recall that you can expand a function about a point using derivatives. Okay, so if the function is sufficiently nice, you can represent x of t as a sum, the following sum. So expand around some point t naught, and it'll be x of t naught plus the derivative of x at t naught times, t minus t naught here, plus a second derivative term times a quadratic function, and so forth. And if you expand this out infinitely for many functions, that's an exact representation of your signal. Okay? And of course, we can verify that all the derivatives work because we know how to take derivatives of polynomials, and we'll see that the derivatives on the left side match the derivatives on the right side. All right? In fact, you may have forgotten, but this is the easy way to verify Euler's formula. So Euler's formula, which we've been working with to represent complex exponentials as sines and cosines, you can validate that the Taylor expansion of both sides of that equation is the same. Okay, so that's one way to arrive at that formula. Now, so we could call this a representation in terms of polynomials. So what we're doing is we're saying x of t, we now have it as a polynomial representation like this. Okay, does this work for every signal? Will you accurately represent an arbitrary signal using a Taylor expansion? I see some shaking no. There's a word for functions that are represented by their Taylor expansion. It's called analytic. So, and I'm only pointing this out. This is not material that's going to be core to what we do in this class, but it's to serve as an example, kind of a parallel to the Fourier transform. This is a transformation that works on analytic functions or analytic signals. And of course, I haven't really explained what it means to be analytic. It's just a math term. But for one thing, it implies that the function is smooth, that all the derivatives are continuous and so forth. So let's say it must be smooth. That's not actually sufficient, but you can think of it that way. If the function is smooth, then it can be represented this way. Now, of course, we see that this representation is all derived locally. So all of these quantities, so in a sense, these are coefficients, right, that we get from the signal. And from x, we get the coefficients, and then we put it in the standard form, and it's a new way of representing x. Now, you might say, why would we want to do this? Well, one reason you would want to do this is to understand how a function behaves locally, how a signal is locally. So it's useful in analysis. It's useful for various purposes. And I'm just giving it here as an example of a different representation of the signal. Rather than just defining it at each point in time, you define it by a bunch of derivatives. All right. Let me give an example of what is a non-analytic function, just to kind of satisfy your curiosity, if some of you are wondering why not every signal can be done this way. Let me do black. Here's a pretty simple example. Let x of t equal t squared for t less than or equal to 0, and 0 for t greater than 0. I can plot this. And we'll have something like the following. And it's flat here. Okay, so that's our signal. It's well defined. But notice that if you take the Taylor series expansion around, whoops, can't see that. Taylor expansion, oh, should be an S, around T naught, for negative T naught, you're going to get x1 of t, let's call that the Taylor expansion around some t naught that's negative, is just going to be t squared. You're going to get something like this. You'll match it correctly on the negative side, but the analytic extension of that's going to be quadratic. Whereas if you did it for t naught greater than 0, you'd get an expansion that was just 0. Right, so you'd match it over. You just get the flat 0 function. Okay, and you're not going to recover, neither one of these is going to recover x of t. All right, so it's an example of a non-analytic signal. All right, so a lot of expansions will work for, a lot of transformations will work for every signal within a certain class of well-behaved. And here the definition of well-behaved for the Taylor series is that it's analytic. Okay, let's talk about another. So we already have talked about the Fourier transform. I'm going to get back to that after I do other examples. Okay, but you understand now that representing a signal as a sum of sinusoids is another transform, and that's the Fourier. And let's look at one called wavelet. So wavelet transforms have been used for the last several decades, sometimes as an alternative to a Fourier transform. It's been used in a lot of image processing applications. And there's actually many different wavelet transforms. And the idea of a wavelet transform, the idea of the wavelet transform is that you represent the signal as a sum of little wavelets. Signal so it's a linear combination of wavelets, and the wavelets have the property that they are finite in duration. So there's many different wavelets, and that defines a new wavelet transform, your choice of wavelet. And you use different shifts in time and different scaling horizontally. So in other words, you represent a signal, you have some wavelet, like I've drawn here, and you take different, you can shrink it horizontally or expand it horizontally, and you can shift it, and you represent your signal as a sum of these different wavelets with different time axis and different shifts. Okay, I'll give a specific example next. And again, we're not going to get into wavelet transforms. This isn't something you have to master. It's just for your information, because they're useful and they're also similar to the concept of the Fourier transform. Similar in that it's a change of representation. Yes? A wavelet is just a signal that has a finite duration. Okay, so it's a signal that eventually dies off. There are many different wavelets. If you look up wavelet transform on Wikipedia, you'll see many different choices of wavelets that are used for actual wavelet transforms. Okay, and perhaps the simplest one is the Haar wavelet. The Haar wavelet just looks like this. Here's 0. It goes. So it's discontinuous like this. Okay. Let me just put the origin there and call this 1 and call that -1 and call this 1 and -1. Okay, in height. All right. So I just drew some rectangular function, and I can use that to represent signals if I add enough of them shifted in time and rescaled in time. Do you have a question? The reason you don't just use a square wave is because what you want, usually they want to take out a DC component, meaning the average value of the signal is the first thing you pull out. And then you want the average of every other wavelet to be 0, exactly. So that it's like you have one extra piece. So basically you're going to add up a bunch of, well, I'll do an example right now. Let's say here's your signal. So this here, I worked out an example. I better use it exactly. Okay. Here's T. So this example goes from T equals, the signal goes from T equals 0 to 8. Outside of that, we'll just assume it's 0. And it's the following. Sorry. Okay, so the numbers here I'm using are this. The height of this is 0.5, 1, 2.5, 4 the rest of the way. Okay, so this is a signal. And then it drops back to 0. All right, now I'm going. The Haar wavelet transform would do something like the following. It would say represent this as a sum of, I'm going to draw 8 different wavelets here off to the right. So one of them goes like this. Actually, I'll do it below. Okay. So one of them looks like the following. Okay. Let me do this. All right. One of them looks like this. Now I'm going to take that wavelet. I'm going to shrink it horizontally and also so it now looks like this. All right, so that's another one of my wavelets, and then I'm going to do that same one shifted. So it's 0 here. Whoops, it's hard for me to draw 0. All right, 0, and then it goes, whoops, right here, it goes up, and it goes down here, like that. Okay, so the same wavelet just shifted over to be in the duration 4 through 8. And I'm going to do 4 more wavelets here. Let's do this. And these ones are going to be, you might guess it, they're going to go, that's 1, that's 1, that's 1, and that's 1. Okay, and just to give you some labels, here's time 0, time 2, time 2, time 4, time 4, 6, 6, 8. And for simplicity, I'm going to assume that the height is always 1 and negative 1. So this height is 1 here, and it's minus 1 there, and same for all the others. Okay. You'll find if you go and actually do wavelets, you'll find that I'm not doing it exactly the standard way. You usually don't make the heights 1 and so forth, but just for simplicity. So we have all of these. I have 7 signals, and you see how they're all kind of derived from each other. And that's the property of the wavelet transform, is that all of your components are derived from one wavelet that's just been rescaled and shifted. Okay. Now, there's one more. I need one more thing, and that's the DC component. In other words, I'm going to add one thing that doesn't look like a wavelet. It's just going to be, I'm going to put it first. Well, I'll put it off to the side, although it's just going to be another signal. Okay, and this one is going to be just 1 the whole way. Okay, from 0 to 8. So that's our 8th component. And the argument is that I'm going to be able to approximate this thing here using a sum of those. Okay, and you probably can see how that works. In fact, it's very simple how to break it up into a sum of these different component vectors. So what I'm going to do is I'm going to have this one be, I'm going to use red here to write the coefficient that I would multiply by that component. I would multiply this by 3. Okay. Multiply this one here by minus 1. This one here by minus 1.25. 0, minus 0.25, minus 0.75, 0, and 0. Okay. Now, if you want to know how I did that, you actually can do this quite easily. What I did for the first one is I took the average of this signal across the whole way, and it was 3. And so that becomes the coefficient for this first one. The second one, I go now and I take this first 0 through 4. I subtract out the part I've already done with the first signal. Okay, so let me construct let me piece by piece construct the sum of these things. Okay, I'll do it on top of our original here. Actually, I wonder if I can make a copy. Yes, that's better. Okay, doesn't look like a copy. Guess not. Oh well. You know what? I'm going to redraw it here. So let's sum up those things that we have. So here's 0, here's 8. If I take 3 times the 1, then I would have 3 all the way across, right? That's what I get from the first component. If I take minus 1 from this, it's going to subtract 1 up here for the first half and add 1 there. So this is now going to be 2, 2, and then it goes to 4. You see how I did that? And this is gone now. So this is the sum of the first 2. Any questions about what I'm doing so far? Okay. And then if I add that third one, I get a 1.25 on top of what it was here. So it's going to be, it's a minus 1.25. So it's going to be 0.75. And then it's going to jump up to 3.25. So the new signal, let me draw in, let me highlight for you that the new signal, the sum of the first 3 is this one. Okay. And you can see that I'm starting to construct what I wanted, this thing up here. If I continue this on, I'm going to get it exactly. In fact, if you want to follow how I decompose this, I explained how I got the number 3. I took the average of the whole thing, right? And then what I do is I subtract 3 out of this first part of the signal, and I take the new average across just the first 4. And that's how I picked minus 1. Because once you subtract 3 from here, the average is negative 1. And that's how I got that coefficient, and so forth. So there's actually an easy way to break this up. Okay. So this brings up a couple of interesting questions. First of all, what could I actually, which signals can I represent with this decomposition? Any ideas? What signals can I represent? Signals that are not continuous? Yes, so you're right. I'm now able to represent signals that have discontinuities. With the Fourier transform, I can, but it takes me using infinite frequencies to do it, right? With the Haar wavelet, I can capture discontinuities even with just a few wavelets. Okay, go ahead.
Are you saying they have to have each time? That's how the transform works?
That they have to have? Yes, that is how it often works in discrete wavelets. Yeah. Okay, so actually you can do wavelet transforms where you do different number of shifts and you don't do just halving, but it's sufficient to do it just half and do the shifts that I've done here. However, I mean, hopefully you see one restriction in what I've done so far. I mean, using these 8 wavelets, can I represent any signal that goes from 0 to 8 in time? Okay, good. So no, I mean, so far I can only represent them if they're flat between the integers, right? Clearly, I can't represent anything that's changing between the integers, so they have to have these flat regions. But what you're pointing out is I could always do more and more wavelets, okay? So I could make them smaller and smaller, and that would allow me to represent anything, actually. So what I would get is if I have some continuous function like this, I mean some continuous and varying function, I could, let's say here's 0, and here's 8, and I have something like, okay. Well, as I add more and more small wavelets, I'm going to get approximations that they're still going to be flat. They're going to be flat on intervals, but they're going to kind of track it like this, right? And this will be the wavelet transform if I only looked at a certain finite number of terms in the representation. Okay. And as I add more and more terms, I match it closer and closer. So in the limit, I do represent the signal, right? So the Haar wavelet transform would be good at capturing, well, first of all, let me make a statement and then we can talk about what it might mean. It would be good at capturing signals that have flat spots and discontinuities, okay? Maybe better than the Fourier transform, but what do I really mean by that? What do I mean by it's good at representing? Because we just said it can represent anything in the limit, so why would we say it's good at representing or bad at representing certain things? What's the purpose of even doing this? It seems like some people have ideas. Like how quickly it converges? Okay. I think that's basically almost exactly the point I'm going to try to make, but maybe I'll let someone else see if they can draw it out. Were you going to say something? Yes, exactly. So you might need less components to represent a signal. And so both of what you both said is really somewhat the same thing. You're saying how quickly does it converge? What I'm going to say is how many of the components are needed to represent your signal, to represent it well. Okay. One thing you often find very useful is if the change in representation, if the transform. Okay. So what I mean by transform is under this Haar wavelet transform, we've transformed this representation of a signal. And if we knew a priori that it was going to be constant between the integers, then we could have represented this just as a sequence, 0.51, 2.54, 44444, and then everyone would know what signal we're talking about. And now we have a new representation. That new representation, all we have to do is list out these coefficients. 3 minus 1, minus 1.250, minus 0.275, minus 0.7500. And again, as long as someone knew that we were talking about this wavelet transform, they would know exactly what signal we're talking about. There are two different equivalent ways of representing it. But notice here that I have several zeros. Okay? And so, in some sense, this transform has simplified our signal. When you end up in your transform space, when you end up with fewer components that are important and a lot of zeros, then there are many applications where you feel like you've got the right representation of your information. Okay, these applications would be, first of all, suppose you were trying to compress the information. Suppose you didn't want to have to write down as many numbers to represent your signal. Well, if you have a lot of zeros, then what you can do is just say, first of all, here are all the zeros, and that doesn't take very many bits to say where the zeros are. And then you just have to list out the non-zeros. Okay, so that's one way of compressing information. If you can transform it to a space that we call sparse. So I'm going to write that down here. Sparse. Probably see. You'll have to forgive my spelling throughout the course. I really don't know if I spelled correctly or not. So I'm basically saying if your new representation is sparse, and that means few non-zeros, okay, then that's often very helpful. And some examples of when that would be helpful, the first one was compression. And the straightforward reason why that can help with compression is you can just you don't have to store numbers for the zeros. Okay. Another reason is, I'll say, pattern recognition and machine learning. Okay, so why would sparsity be helpful for that? Well, usually what you're trying to do is you have some information and you just don't know how to make sense of it. All the information is there in your data, but you want to make sense of it in some way that you can make decisions based on it. If you can transform it into a representation that's sparse, that only has a few key components, then you usually feel, first of all, intuitively, you feel like you've actually got to the essence of what you're looking at. That now you know the structure of your information because it's completely made up by just a few key components in your new domain. And that's often the first step of machine learning, is to take your data and extract from it features, and you hope that you got the features that are most important in your data. And so that's very related to sparsity. If you are able to transform it into and get sparsity, then you'll be successful as that being the first step in your decision-making machine learning process. Another thing that's very much related to that is called denoising. So sometimes you have some data that's noisy. Imagine actual audio that has noise, background noise in it. And you expect that what you're listening for is actually very structured. For example, if you're listening to someone's voice, that's actually very structured in the Fourier domain. It's sparse in the Fourier domain, and you've seen that in your labs, and you'll see it again and again. That when you take the Fourier transform of instruments, of voice, they have some key component frequencies that are spread out. Okay, and that's what I mean by sparse. And when you add noise, the noise is generally assumed to be kind of all across all spectrum, not structured. Maybe it has some structure, but not as structured as what you're listening for. So one method of denoising is to take your signal, which is not going to be sparse because the noise is going to be everywhere, but you take the small components and you say, well, these are probably noise because the big components are parts of the signal I'm actually looking for, and the small ones, because of the sparsity, are probably noise, so you zero them out. That's one method of denoising, to try to get rid of the noise and keep the signal. Okay. So this is just somewhat of a philosophical discussion in this lecture, is why would you transform your data? And I would say sparsity is probably the number one thing you're hoping for when you transform your data. Okay. Now we're going to find something else. is, so the Fourier transform is going to be interesting and actually fundamental for reasons aside, in addition to sparsity. Okay. So the Fourier transform does give you sparsity for many important signals. In fact, in Shazam, that's the entire reason you use it, is because when you do use the Fourier transform on your on a music signal, the music ends up giving you these sparse sort of fingerprints in the Fourier domain, and you can use that to match signals together. Okay, so sparsity is the entire reason that you would use Fourier transform for Shazam. But we will see that actually the Fourier transform, the reason that we're so focused on it and that it's so broad in application is it has other important reasons aside from sparsity why it's the right way to look at your signal for certain problems, in particular for control problems. Okay, so so that's things to come over the next several weeks. Hopefully you'll gain an appreciation of why Fourier transform is the right transform for many applications. Okay, but notice one thing wavelets gives that Fourier doesn't. And those who have done the lab will appreciate this a little more. If you do a Fourier transform on your on a signal, you learn which frequencies are in that signal, but those frequencies endure for the whole duration of of time. And so it's not immediately obvious when those frequencies are occurring in your signal. Okay? By looking at a plot of the Fourier transform, it's not immediately obvious when those frequencies happened. I mean, the information's all there, but it's not something you're going to be able to see by eye. On the other hand, in the wavelet transform, you see these wavelets don't endure the entire length of time. So they give you, at the same time of sort of giving you, they give you a temporal resolution, okay, spatial resolution, meaning depending on which wavelet it is, you know whether that signal occurred later or earlier. And they also give you sort of a frequency resolution in that the wavelets that have been shrunk sort of represent higher frequency components. Okay, so simultaneously from the wavelet transform, you get some timing information and you get some frequency information, and that's one of the key features of why people like to use the wavelet transform for certain applications. Okay. Any questions about this? Actually, let me pull up an example of an image, some simple image processing. And actually, Sai, the TA, gave me a great example last year, and I didn't bring it today. Maybe next time I'll bring it. It was a project he did as an undergrad using the wavelet transform for compression and denoising or something like that. So maybe I'll bring it in next time and just to show some examples. But off the web, I can find one using now it's an image, so these wavelets are two-dimensional. But this is using, again, the Haar wavelet transform. So it's going to have, the wavelets are going to have flat sections, like rectangles that are flat. Okay? And what's happening here is this first part, this picture of the cat, after doing the wavelet transform, you get a whole bunch of coefficients. If you need a lot of wavelets to represent this cat perfectly, pixel by pixel. And so this here, which probably doesn't make any sense to look at for the untrained eye, is actually all of the coefficients for each one of these colors represents how much of a certain wavelet is in this picture. Okay. Now notice what they do here. They say, if we throw away 95% of the coefficients, so black now is 0. So of all these coefficients, they threw away the smallest 95%. They're only keeping 5% of these coefficients. And then they reconstruct. Of course, you're not going to get it exactly. You get something with all these artifacts, and you can see these artifacts are shaped like the Haar wavelet, right? But that still is a pretty interesting that you can get something that looks quite similar using only 5% of the wavelet coefficients. Okay, so there's an example of kind of sparsity or near sparsity in the wavelet domain. Here's another one. Same thing, threw away 95% of the wavelet coefficients. So the original picture is on the left and the new picture is on the right. Okay. Now, the Haar wavelet is not the most commonly used for images. There are other wavelets that are not so flat, okay, that are used more often. But this was the simple one to demonstrate. Okay, I have another demo, but I'm willing to answer any questions about wavelets. We're going to move on from wavelet, never to return. Let me point out a similarity before we move on between the wavelet transform and the Taylor expansion. Both of them are represented as a sum. So you have components. Here the components are polynomials. And you sum them together to get the original signal. So this is a linear operation. Given the coefficients, it's linear with respect to the coefficients. Okay? Because it's just this sum. We'll talk more about linearity soon. Well, the wavelet transform is similar. In fact, every transform I'm going to talk about is done this way, where the new signal, where is it? Where we sum the components to get back our original signal. A transform doesn't have to be done that way. It doesn't have to be linear. But all the ones we're going to talk about here are linear. Okay, so you sum the different components after scaling them. So suppose, I'm going to now move to discrete time signals. Everything I've been drawing is continuous time. But let's talk about discrete time. The same type concepts. The reason I'm going to do that is because I have a MATLAB demo using vectors of numbers, and which is going to be discrete time. Okay. So let's talk about what does it take to, what properties do we need of these different signals in order to allow us to use them to reconstruct anything? Is this wavelet just really special that it allows us to reconstruct any signal? Are signs really special that we can use them to construct a signal? This actually came up. There were questions on Piazza. Many of you have asked this question. Why can you construct a signal from adding together sine waves? And right now I'm going to tell you that it's not actually anything really special about the sine waves. You could do this with many different options of signals, components. And just to drive that point home, I hope this example makes sense, I am going to, I forgot I have to download my code. Hold on. Okay, so what I'm doing in this code is I'm going to create a signal, which I call x. Okay, so this first part here, this is x. Okay, now I'm not plotting the lines between the points because then the smiley face wouldn't be so visible because it would go down and jump up and come back down. You see, this is a signal, a discrete time signal. So we have here are the points at each the value of the signal at each integer are represented with circles in this plot. Normally you are probably more used to connecting these with lines, right? But it's discrete time, so it's only defined at the integers. So I can plot it this way just as easily, and it's just a sequence of points. Does this make sense? This is a plot of the signal over some duration from 1 to 15. We'll assume it's just 0 everywhere else. Okay, now what I've done is I've actually randomly, using the random number generator, generated some vectors, some signals that I'm going to use as my components. I'm going to try to use these colored, it's a different color for each one, these randomly created signals, and I'm going to try to sum them up in just the right way to create any signal I want. In particular, I'm going to try to recreate x on the left by summing these things together. And here, just to avoid, here I did put the lines just because if I only had circles, this would just be a big mush of circles. Okay, so, but remember, the value at the integers is all that's important here. Okay, now, am I going to be able to do it? I just randomly created these signals. So how do I know these signals are going to be so special that they're going to allow me to reconstruct any signal I want? If I have enough. So how many would you expect me to need? How many? Well, I mean, I can make an infinite number of signals, but let's say my signals are all restricted to be defined on the integers 1 through 15. In other words, I'm only taking vectors of length 15, right? So if I only want to be able to reconstruct any signal that only lives between 1 and 15 on the integers, then the question is, how many do I need? Yes?
15 as long as they're not multiples.
Perfect. So as long as they're, we would say, linearly independent, which would mean that, for one thing, they're not multiples of each other, and that you couldn't make any one signal by summing the rest together. Okay, so as long as these are linearly independent and I have 15 of them, then I can use that to span the whole space and create anything I want. If I generate them randomly, then they're going to be linearly independent. So this should work. So then I have another plot that's going to show me creating that signal. Now I have to do some math to figure out what are the coefficients of each of these. Of course, it just takes linear algebra. It's just a matrix inverse. Okay, let's do it. So here is our reconstruction. So what we're going to do, I'm going to spread this out a little bit. What I have here is on the left, I have the individual component that I'm going to add these components in one at a time. So here's the component I'm adding in right now with the proper scaling. Over here, what I'm doing is just highlighting which of the, which of these signals. I've just made it bold so you can see it's the same thing on the left as it is here. In other words, I'm taking this component with the optimal scaling, and that's what this is right here. Okay, and I'm going to add that into the 0 vector. So blue is the new signal I've created. This blue is exactly this, with the lines not showing. And of course, notice these axes. Oh, these axes are the same. How come it doesn't look the same? 0. Oh yeah, it is the same. It's just that you can't see the circles down here. Okay, so these are the same so far. Green is showing what the signal looked like before adding that one component. So let me click again. I'll add another component. Okay, so I'm adding this thing. So the green is what we had previously, and the blue is what we have once we add this new term in. Making sense? So let me just keep clicking. Okay. So remember, blue is where we are so far after adding 3 together. Okay. Still looks totally chaotic. We've already done like 6 or something. Starting to get there. There we go. So we got exactly the signal we wanted by adding them up in the proper proportions. Okay. So this is just to point out that in some sense, there's nothing special about sinusoids or Haar wavelets. I mean, there's something special. They need to be linearly independent, and they need to be complete, meaning you have to have enough of them to span the entire signal space. But if you're in discrete time, then you only need as many as there are points in your signal. There were 15 points in our signal. We only need 15 different components that are linearly independent to span that whole space. Okay, so, all right, did this make sense? Any questions about this? Okay, so if you, in general, meaning like the example I just showed you, figuring out the coefficients of each of the vectors involves interactions between the different what I'm calling basis vectors is what I was calling components a moment ago. Okay, the component vectors that we're going to split our signal into. Figuring out their coefficients, there's a lot of interaction between them. And let me, by example, show you what I actually mean by this. Mathematically, I've already mentioned this is just a matrix inverse. Oops, mathematics. But if you look at the operation of inverting a matrix, it's somewhat complicated. And so let's just consider vectors in 2 dimension. Now, some of you might be saying, I haven't taken linear algebra, and I feel like we're talking about too much linear algebra here. I'm not expecting you to necessarily know linear algebra. If you do, great. Maybe some of the things I say will have a deeper meaning to you, but you're not going to get behind by not knowing it. But basically, signals, we can think of a signal, even a continuous time signal, abstractly as a vector. Okay. Now, discrete time signals, it's more easy to imagine those as vectors, especially if they have a finite length. In MATLAB, in your labs already, you were creating vectors that represented discrete time signals. Okay. So, of course, if you have a discrete time signal that goes on forever, that's an infinite dimensional vector. Okay. A sequence of numbers. If you have a continuous time signal, well, now you have an even larger dimension of vector, and it may be a little bit abstract to think of that as a vector, but the math works out just like it does for vectors. So let's think about a 2-dimensional situation. And here's the origin here. And suppose you have some signal x in 2-dimensional space. You can think of it as a sequence of 2 numbers. And suppose we want to take 2 vectors. Now I'm going to start calling them basis vectors. I was calling them components before. Okay, we have 2 basis vectors, meaning they're, here they are. Call one v1 and one v2. And these are linearly independent. It's in a 2-dimensional space, so they span the whole space, meaning that any point in this space can be represented as a sum of these 2. Okay, and we can see by inspection how we would have to multiply them in order to get them to add up to x. Okay, we would have to do the following. We'd have to multiply this one to make it about that long. We'd have to multiply this one to make it about that long. And the reason is that once we've scaled them, we would and then add them, we want them to add up to x, right? If you add these 2, you get x. All right. So by I, we're able to see how we would decompose x into v1 plus v2, what the coefficients would be. And the coefficients would exactly be whatever you need to multiply by v1 to get it to be this long. So get it to be this long here. And whatever you need to multiply by v2 to get it to be that long. Okay. Now let me redo the same example. Here's 0. Here's x. And I'm going to keep v1 exactly the same. v1, but I'm going to change the other basis vector. Okay, I'm going to make it like this. And I'll call this v2. Okay, again, it's linearly independent, so it still spans the space. But now if I try to figure out what the coefficients have to be, I would get something like this. This one I'd have to multiply to be about that long. And this one I'd have to multiply to be about that long. So when I add these end to end, they get x, right? Now what I want you to notice is that even though I did not change v1, when I decomposed, I got a different coefficient for v1. Here I had to scale it much longer. And that was simply because v2 changed. Okay, and that's what I mean by there's an interaction. In general, there's a lot of interaction. Figuring out the coefficients, it doesn't just depend on v1. The coefficient for v1 doesn't just depend on v1 and x. It depends on the other vectors as well. Okay? So that brings us to this. orthonormal basis. You may have been wondering, why did we do all this orthonormal stuff in the homework? Okay, so if your basis is orthonormal, then actually finding the coefficients is extremely easy. All right, orthonormal in this picture would mean these things are orthogonal to each other. All right, so here's what we say. Okay, so here's what we mean. Let's say that, again, we're going to represent a signal x of n as a sum. You can think of x of n as a vector, if you want, as a sum of a1, some coefficient a1 times our first basis vector, or basis signal, plus another coefficient times our next basis signal. And we can use the notation of a sum like this for k equals, well, let's say of ak vk of n. Okay, maybe this might have to be an infinite sum if we were talking about all possible discrete time signals. Okay, so this is what this is a representation, a change of representation. We're changing xn to a bunch of coefficients, assuming that we all know what the vk's are, and and this is combined in a linear way. So this is a linear transformation. Now, if the set of vk's is orthonormal, then it turns out it's very straightforward to figure out what the a's are. AK just equals xn inner product with vk. All right. Remember, we had to have, first of all, the definition of orthonormal required that we had some inner product. Okay. So whatever inner product you use to show that they're orthonormal, then that's the same inner product you should use here to find the AKs. Which means, another way to write this is that x, the signal x, is the sum of, I'm going to replace AK with what we found it to be here, xn vk of n. So this is just a number. This inner product is just a number that depends on which vector you're looking at, which k, times vkn. Okay, so here's the change of representation. This happens because it's orthonormal. Let's actually just verify that this is actually true. Okay, to verify, let's say that we have AK equals, or actually let's just do this. We have, let's write out this inner product. Replacing xn with, we're claiming that xn can, we know that xn can be split up into this new basis, okay? Because we're assuming it's orthonormal and complete, let's say. Then let's write xn in that other representation. It's a sum of these AKs. Whoops, I don't want k there. It's a sum over I of AI VI of n. Okay. Now, one thing you hopefully have noticed about inner products, and this is true for all inner products, but in your problem set you did inner products that we defined using integrals and so forth, and you'll probably notice that they're linear, meaning that if you have if one of these things is a sum, then you can split it as a sum of inner products. Okay. If you don't believe me, go back and look at our definition of the inner product using the integral, and you know integrals are linear, so you could definitely split it up. It's going to be true for any inner product. It's a requirement of inner products. So that means I can write it like this. The inner product, so it's a sum of inner products. And now we know this is orthonormal, so we know that this inner product between two of these basis vectors is either 0 or 1. Right? It's 1 only if I and k are the same. If it's the same basis vector, otherwise it's 0. That's what it means to be orthonormal. So, therefore, every term here is 0 if I does not equal k. The only term that survives is the one where I equals k. And we just get ak. See that magic? Okay, so we just verified that ak, in fact, equals this inner product. All right, so that's what you get by using orthonormal basis rather than just an arbitrary basis. You get this very easy way of finding the coefficients. It turns out that with the wavelet transform, people usually design the wavelets to be orthonormal as well. All right. Great. So let's get back to the Fourier stuff. And in the Fourier series, first of all, let's check whether our components are orthonormal. So for the continuous time, we have, let's define our v's. Let vk of t equal these signals. E to the I 2 pi k over cap t times little t. Okay? First of all, this set, the set of vk's, these signals, are periodic. All of them are periodic. And in fact, they all have a period of t. Okay? That's not all of their fundamental period, but that's okay. They all have a period t. Now we have, let's use the inner product we defined for periodic signals. So use the periodic inner product. Which said that x and y, the inner product between x and y with period t is 1 over t integral from 0 to t. Okay, so that was our inner product. So let's just check, are these really orthonormal? All right, and we will check it by just taking the inner product. So we'll do v k1 of t, v k2 of t. Take that inner product. 1 over t, integral from 0 to t, e to the I 2 pi k1 over t, t. And then our second signal, e to the I 2 pi k2 over t, t. We conjugate the second one, dt. All right. Now the conjugate is just going to bring a minus sign into the exponent. So this is going to be 0 to t, e to the I 2 pi k1 minus k2 over cap t times little t. Okay. So we need to do this integral. Notice that this equals, we do a 1 over t times, and then let's do this, 1 over I 2 pi k1 minus k2 over cap t times e to the I 2 pi k1 minus k2 over cap t t evaluated from 0 to cap t. Okay? However, you have to be careful with this integral. By the way, now you see why we like exponentials. Integrating exponentials is always nice. Okay. Sines and cosines aren't bad either because they are exponentials. But this isn't always going to be true because, look, I might have written something that doesn't even make sense. If k1 equals k2, then this is 1 over 0. That doesn't make sense. So for that case, we should look back here and say, well, if k1 equals k2 and this is 0, what is the integral? It's e to the 0. What's the integral of e to the 0 from 0 to t? That's cap t divided by t, so it's 1. So this will be 1 if k1 equals k2, and it'll be this thing up here if k1 does not equal k2. Okay, so you have to be careful with that. Now, what does the top come out to? It's going to be the following. Notice that, if we evaluate from 0 to cap t, this is going to be 1 over t times 1 over I2 pi k1 minus k2. I'm going to delete the 1 over t because those cancel. Okay. Parentheses e to the I 2 pi k1 minus k2 minus 1. Okay, so notice we got a lot of canceling of t's and 1. Okay, and what is the top here? That actually equals 1, right? Because k1 and k2 are integers. That means that this is e to the I 2 pi times an integer. And that's always 1. Okay, so that means this whole thing equals 0. And that's what we need for orthonormal. Okay, so these are orthonormal basis. Okay? It's a bit painful, but I will also repeat the same thing for discrete time. The reason I'm going to do that is just so you all make sure you're all familiar with the geometric series. Okay? That way, when you encounter these problems in real life and in the problem sets, you don't run into any hang-ups. All right, so discrete time. So here what we're going to have is our VKs, our basis signals, and I use a bracket n to just show that there's a discrete time signal. This is going to be e to the I 2 pi, same thing, but with a capital N that's an integer. Integer n. Okay, t didn't have to be an integer, but for discrete time, n needs to be an integer. And we look at these signals, and the first thing we're going to notice is that, of course, this set of signals they're all periodic. With period n. Okay. Now let's take the periodic inner product. I never actually defined that in class. It's going to be basically the same way. Define. Oh, hold on a second. I should put a little t there, right? Okay. So we're going to define something here that x, y, t for discrete time signals is going to be 1 over n times a sum from n equals 0 to n minus 1. Okay, so the same thing, sum instead of an integral, and the only point to notice is you just sum over one period, which means you omit the endpoint. You don't do the endpoint twice. Okay, the only technicality. Okay, so again, we're going to say, is this set orthonormal? Now, here's the catch. This set is orthonormal if you only take n of the points. So from k equals 0, let's say 0 to n minus 1, that set of signals is orthonormal. You'll realize, if you look at the math carefully, that if you take too many, you're going to get to signals that are no longer orthogonal. Okay, but I'm not going to worry about that right now. So just take the first n of these basis vectors. Let's check if they're orthonormal. And I claim they are. All right. And to check, we just do the following. Boy, I'm running out of time. I'm going to speed up a little bit. All right. We do, again, vk1 of n, vk2 of n equals 1 over n, sum. Okay, and I'm going to write this with a parentheses just to make it clear how I'm going to use the geometric sum here. So this I can write as e to the I 2 pi k1 minus k2 over n as a number to the little nth power. Okay, so this is a constant with respect to little n. It's just a number. And we have a geometric series, which is very useful. And the geometric series says that if you sum n equals 0 to something like kappa n minus 1 of a number a to the n, that's going to equal 1 minus a to the cap n over 1 minus a. And therefore, if you sum to infinity, that's something we'll often want to do. This is going to equal 1 over 1 minus a as long as, if and only if a, the magnitude of a is less than 1. Because notice, in order for this to converge, that a to the cap n better go to 0. Okay, so the magnitude of a should be less than 1. Now notice there's one catch with this geometric series. Again, this, as I wrote it, would not be well defined if a equaled 1 exactly, because then the denominator is 0. Okay, so this is true if a does not equal 1. Okay, and if a equals 1, then it's straightforward. 1 to the n is just 1. So if a equals 1, then this sum is just cap n. Okay, so that's the geometric series, which we'll use right here. We'll use that on here, and you will notice, oops, so let's say that equals 1 over n. 1 minus this quantity to the nth power, right, over 1 minus that quantity not raised to the nth power. Okay, now, here's the trick. And the trick is that, and this is only, again, if k1 does not equal k2, because otherwise we saw that then this whole quantity would be 1, and that was the special case for the other form of the geometric series. For that other case, I'm not going to do it because it's too easy. If k1 equaled k2, then, oh, that should have a minus sign. If k1 equaled k2, then this is just going to be n divided by n. It's going to be 1. So they are normal, right? If k1 doesn't equal k2, then we have this formula. And notice that the n's cancel. And also notice that e to the I 2 pi times an integer is always 1. Okay, so it's 1 minus 1 equals 0. So orthonormal. Okay. So now we know these sets of signals are orthonormal. Why did that matter? Well, because notice now I'm going to justify the Fourier series equations. So therefore, we arrive at the Fourier series, which is that the coefficients for each of these, remember the Fourier series in continuous time was that x of t equaled a sum, an infinite sum, of some ak's times e to the I 2 pi k over t, right? But in our new notation, if we want to use v's as the notation, we can say that's just a sum, a linear combination of the v's from above, vk of t, right? That's how we define them. And that's an orthonormal basis. So we can arrive at the ak's just by saying ak then should be the inner product between x of t and vk of t, the periodic inner product. Okay, and that equals 1 over t, integral from 0 to t, of x of t v conjugate of t, right, vk conjugate dt. Which equals, I'm going to do it in 2 steps, 0 to t, x of t, and this thing, vk, was e to the I 2 pi k over t conjugate. But the conjugate just makes it negative. Okay, and that's the equation we had for Fourier series. So there, now you know why it's a negative in the analysis equation. And it's not negative in the reconstruction equation. It's because it was the inner product had a conjugate. Okay? We could do the same thing for discrete time. It would be exactly that you'd plug it in and you'd get the same thing. The formula I gave you for the analysis equation for the discrete time Fourier series is just an inner product between x and the basis vector. Okay? Now, the last few minutes, I'll start talking about something we'll carry over to next time. But we said that the Fourier series is to represent periodic signals. So if you have something like this that's periodic, okay, then we know it can be represented by a Fourier series. So you choose one period, like this, all right? And you calculate, actually, according to the definition I gave you, you take the period from 0 to the fundamental period, okay, and you use the integral to calculate the Fourier series coefficients, and you get sinusoids that add up to this, right? Of course, you only used this signal in this finite duration to calculate the Fourier series coefficients. So an equivalent way to think about the Fourier series is you could also think that it's meant to deal with finite duration signals. So imagine that now you're interested in signals that only have a domain from 0 to cap t or on any finite duration. You could always just think of, you could use the Fourier series to represent this signal and its periodic extension. And if you are only interested in that duration of the signal, then another perfectly valid way of thinking about the Fourier series is that it's used for either periodic signals or finite duration signals. And the reason this is important is because in your labs and in MATLAB, you're always going to be dealing with finite duration signals, right? And yet we're still going to be taking Fourier transforms. And so just realize that it's equivalent to doing a Fourier series of the periodic extension of whatever your finite duration signal is. Okay, so because once you reconstruct with the sinusoids, you'll get something that is periodic. Okay, I know I'm going a little bit fast because I want some of you to have this in your mind when you do the lab. Yeah. Well, let's see. What can I say in the... Okay, I know what I can say in the last 2 minutes. Actually, I don't know what I can say in the last 2 minutes. Maybe I'll just stop. So what we covered won't necessarily help those of you who are doing the lab today and tomorrow, but I think we've figured out the kinks anyway on getting you to be able to complete the lab. So we'll stop here